I took 14.
Okay. So we need to cover a few more things that we didn't quite wrap up last time. We are going to move into the next section today, which is 7.5, I believe. No, 7.7? 7.7. So how did it go in terms of the homework? How was the graphing?
Easy.
Easy? I thought they were pretty easy, actually. Were they really easy?
Well, the shifting one.
Yeah, the shifting. So that's what I didn't talk about. So I want to talk about the shifting, and then get some other formalities out of the way, and then we'll move on to 7.7. All right, so we should do one like what? You want me to do one like what?
Like 85, but with shifting at
85. Oh, okay. Yeah, I see that. All right, so last time what we learned was that your basic sine function starts out at 0, ends at 2 pi. But more importantly for us, that there were those 3 marker points, those 3 x-intercepts that helped us graph everything, right? And that we could break this number line up and basically get these 4 sections. And that getting those x-intercepts sometimes required a little bit of work. We had to find the average and all that stuff. And then we determined that cosine pretty much worked out the same way. There were 4 important sections that our x-intercepts happened at the first quarter mark and the 3/4 mark, and that it would go like this and like that. So this is y equals cosine x. So what we want to discuss now are, again, some formalities. Talk about domain, range, amplitude, things like that, just so we have them written down. So for this function sine, the domain of sine is what? So what are we allowed to plug into in for x into the sine function? So can I plug in positive numbers? How far can I go? Forever. How about negative numbers? This does go backwards, right? Because remember, negative would mean negative angle, and that's okay to have negative angles. So this sine wave goes off to the right forever, and it goes off to the left forever. So the domain is negative infinity to infinity, or all real numbers. Now the range has to do with the output of the function. And we know by looking at this, for the basic sine function, it goes, the lowest value we ever get out is -1, and the highest value we ever get out is 1, right? That's a little off there. Okay, so the range is between -1 and 1. And I put brackets on the -1 and 1 because that includes those 2 values. You can actually attain -1 and 1. The amplitude, I'm just going to put amp. The amplitude of the basic sine function is what?
0 to 1. Is it positive?
The amplitude is always a number. It's just a number. It's not an interval. So it's just 1. It's the distance from here to here, right?
Right.
Or it could be like this divided by 2, either way. So the amplitude is 1. And then what about the period? So we know that the sine function repeats itself, right? How long does it take for it to start repeating itself? What's the length of this? 2 pi, right? Starts at 0, ends at 2 pi. Again, remember, I am going off of the basic sine function. I haven't changed that to like 3x or put a different number out here. That's your basic sine function. That's your domain, range, amplitude, and period. Yes? Now, in terms of cosine, what's our domain? Does it go out forever?
infinite.
Yep. Goes that way forever? Yep. So the domain is the same, right? What about the range?
The same.
Same as this one. How about the amplitude? Same. Period. Starts at 0, ends at 2 pi, right? Then it starts repeating itself. So same period. So sine and cosine have exactly the same domain, range, amplitude, and period. Now, what if we change it and we no longer have the basic sine function and we have something different? Like, let's say we take y equals a sine of, and I want to use the same letters they use here in the book. They use omega, I think. Where is it? Yeah. They use the Greek letter omega, which looks kind of like a W. Omega x. So what happens if I change that? If I make the number in front of the sign like a 4 maybe, and here I put like maybe 3. How does that change our domain, range, and period? Well, the domain is going to remain exactly the same because we can plug anything we want in. The range, however, is going to change because that number in front, A, is going to make our amplitude larger or smaller. It could be smaller. It depends on what A is, right? So our range is actually going to change. Instead of going from -1 to 1, what's it going to go to? What do you think? Whatever A is, right? So it should be like from negative capital A to like positive capital A. So if that's a 2, then we should go between -2 and 2. And then the amplitude will always be the absolute value of that number out in front, A. So if this happens to be like -1/2, your amplitude would be +1/2. Now the period, we have not discussed this. How is the period impacted? What makes the period change? Now the period, remember, is the distance it takes to go and complete one full cycle. And it turns out that there's a very simple formula to calculate the period. The period is always just going to be 2 pi divided by omega, which is the number in front of x. So maybe put a little star next to that because that's an important formula that we will use. So look at this one right here. This basic sine function, we had A is 1, right? And then omega is the number in front of x. That's also 1, wasn't it? So if I say what's the period of this, you take 2 pi and divide by 1, which is just 2 pi. But if we had something like, what if this was 2x? What would the period be? If that was 2x, it would just be pi, right? So that would actually kind of like shrink it down, and it would do a full cycle in a shorter amount of time. Now, what do you think happens if I change this to a cosine? Does anything here change? Domain should be the same. Range should still be -A to A. Amplitude should still be absolute value of A. And the period will be the same. So this works for both this and this. All right? So for both of these scenarios, you have this. Now what we did not talk about, and it was on your homework, was vertical shifts. Vertically shifting your graph up and down. All right, so let us discuss that now, right? Notice this right here, there is no vertical shift. So let me show you how we get vertical shifts. And then we'll talk about all the other stuff and see if we can't figure it out. It's going to be a little strange, but let's say we have, let me do an example first. Let's do something like the homework. Y equals -1/4 cosine of, how about 1/5 pi x and then -2. Okay, that's good. I look at that problem right there and I say that's a decent test problem right there. I could put that on a test and feel good about myself. as opposed to like y equals cosine 2x. That's not so much a test problem, right? So see how we deal with this. Well, back in college algebra, we learned that when you take a function, right, in college algebra, we learned that if you take a function and you add a constant to it, all that does is moves it up by this constant. Or if you take a function and subtract a number from it, right, this goes up, this one goes down. So it just takes the whole picture, moves it up or down. Same exact thing happens here. You have this trig function, this cosine function right here that has amplitude and period and all that stuff. And all we're doing is just taking every point and moving it down too. So the way that I suggest graphing this is to ignore the -2 for now, graph this, and then just move, at the very end, you're just take every point and move them down too. And then draw a final picture, which is the way I did it in the homework. So y'all want to go for this one? Okay. Let's see if we can draw this. Where do I start?
Set your argument equal to 0 and 2 pi.
Set the argument equal to 0 and 2 pi. Right? That's what we do for all sines and cosines. So my argument is just this piece. 1/5 pi x. Set that to 0. Also 1/5 pi x equal to 2 pi. Now, this is the first step, but I also think you should be thinking, right, that we know that cosine functions, missing one there, do that, and we're going to be interested in getting those two x-intercepts, right? Okay, that the x-intercepts don't occur at the ends, they occur at the first quarter and 3/4 marks. Okay, so that's kind of in the background as I'm doing this. I set this equal to 0, and my only answer here is 0. And then I set this one to 2 pi, and I've got to do some algebra here. So what do you get for x there?
I think it's
10?
pi.
Do we still have a pi?
I'm sorry, it's just 10.
Just 10, right? So we could divide pi on both sides and kill them off. And then multiply both sides by 5. And you'd get x is 10. And then what? What should I do next? Draw it? Okay. So I'm going to start drawing. And I'm going to mark on this graph at 0 and at 10. Now, am I going to put dots or am I just going to somehow mark them? Just somehow mark them, right? So here's 0 and here is 10. See, I'm not putting dots because cosines don't have the dots at the ends, right? They have them at the quarter marks. So I will now split this in half. That's 5. Split that in half. That's 5 halves. Split that in half. That's 15 halves. Notice I'm not using decimals. And I'm, again, trusting that you could get those fractions now on your own. You could do that? Okay. We good? Now I should start marking my x-intercepts. I know that they're here and here. Now, I still have to move everything, don't I? So this is a temporary graph. So when I do it, maybe I do it in a different color, or I do it very lightly with my pencil or something. I do it so I remember this is not going to be my final picture. But this is what it would look like had I not had that -2. And then, what was next?
So do you want us to draw 2 or just the one?
I would like to see all of your work. Like I'd like to see, I'm going to draw this one right now. When I do it, I'm going to do it dashed. I think you should do that also. It shows all the intermediate work that goes into it. But what should my next step be? Do what?
Amplitude.
Amplitude, this thing? So let's make sure we're all comfortable with the next step. Because this is where I think some people could get in trouble. What did I tell you you should do next?
Multiply with 0. The argument, right?
Not multiply. I think what you're saying. You're saying
Sub-0
Set it
the
to-
argument.
substitute 0 into the function. So in other words, we're trying to figure out if our graph did this or if it did this, right? And I said that yes, there are ways you can look at the amplitude and determine that, but it's dangerous later when we do phase shifting, which is left and right shifting. That can become dangerous. So I always like to go with the fail-safe method that won't ever break down on you, which is to just plug a point in and just test the function. So I'm going to plug in 0. I'm not plugging in 5/2. Why? Why am I not doing this one? That's an x-intercept. I know the answer is 0. Okay? I know I'm going to get 0 there. So there's no sense in me plugging that in. Now, had this been a sine function, it would have been different. I would have had dots here, here, and here, and I would have plugged in 5/2, right? So because it's cosine, I'm going to pick out 0. I'm going to plug it in. Now, when I plug it in, I'm still not paying attention to the -2. Okay? I'm not going to do that till the very end. So let me plug in. I'm going to do y equals -1/4 cosine. Now, when I plug 0 into this, it kills everything off, doesn't it? I just get cosine of 0. And cosine of 0 is 1, right? And so I get -1/4. So that means at 0, I have a -1/4, and I told you last class it doesn't matter where you put it. As long as you label it, we're good. If that's -1/4, +1/4 will be up here. And now I can put all the other dots where I need them. So where should I be placing dots here? You just need that point. That's it. Everything else should follow the pattern here. So above the 5 at 1/4, right? Okay, and then at 10, where? Below, down at -1/4 again. And then it's going to be like smiles and frowns all the way across, make it look like the green one here. Yes? Okay, here we go. Doing it dotted. There it is. So that would be just that, right? That's what that would be. But now I want to do -2. So -2 means every single y coordinate, every single y value needs to be taken down 2. So this can be a little bit tricky. Let's see here. I need to move this. I need to extend my y-axis down.
Could you just change what you marked the y-axis point in? Like just subtract 2 from your 1/4 and then not bother moving the...
Subtract, you could, but then you have to change your x-axis too.
That as lower? I don't know.
You could, but you would then have to move your x-axis too, right? Like everything would have to move.
Well, I mean, is it necessary to have the x-axis drawn? Couldn't you just label it as being not the x-axis anymore? Like, now it's at the point...
I think what you're suggesting is like make that like this -2, this -2, this -2, and just be done.
Yeah.
Yes? You could. You could. The only reason I'm going to say not to do that is because if you ever had to do 2 graphs on the same coordinate plane, you're not going to be able to take that kind of shortcut around by just changing. Because you know what I'm saying? Like you'll have 2 of them, so you have to have them relative to one another, and you won't be able to do that. So I'm actually going to move it. I'm going to move each point down. So what would happen if I took this point right here and moved it down 2? Where would I be? What's that new y coordinate? Well, I'm taking -1/4 and I'm that's not a 4. -1/4 and I'm subtracting 2, which is -1/4. What the heck's going on? Minus, I need a common denominator here. So like 8/4. That's a 4. -9/4. Okay, so this is -9/4. All right, that fair? This point comes all the way down to here. And this point here was also at -1/4, wasn't it? It's going to come all the way down there also. Okay? How about these x-intercepts? They were at 0, right? Now they're going to be down 2. So -2. So, and I think I'll be really precise here. If I'm saying that that was down 2, then this point down 2, oh, that's pretty close actually, would be there. and then this x-intercept right here would be here. Following me? We still need this point right here, which should come down to here, but what is its value? Right there. What is it? -7/4? So what you did is just did 1/4 minus 2. Okay, so -7/4. My x-axis was here, wasn't it? I don't need to do this, but I'm going to anyway. I'm just going to bring my x-axis down here, just so you can see. Like that's kind of where the x-axis went. And now I'm going to draw the picture. So this is my graph. Something like that. This whole graph moved down too. That okay? I have a few more questions off this graph. For that function up there, what is the domain? For this right here, the whole thing. What's the domain of this function? Negative infinity to infinity. You can still plug in anything you want, can't you? I mean, like this graph continues this way forever. And it continues this way forever, right? Like that? Yes?
Will there ever be a time when it doesn't go on forever?
For a sine and cosine function, unless you are told there's a restriction on the domain for some reason, then it should go forever in both directions. So it's kind of like, you know, polynomial functions in algebra, like x squared plus x. All polynomials went to the right forever and to the left forever. Unless it's in a word problem and it doesn't make sense to have negative x values. Otherwise, the domain is everything. All right, what about the next part? The next part's a little harder, range. It's a little harder to just look at this and get range. You can get it by just looking at it, but the picture really shows it. So what is the smallest y value we have? -9/4. And the biggest? -7/4. So my range is between -9/4 and -7/4. Make sense? How could we have gotten it from here, though?
Just subtracting the 2 from the 1.
Yeah, you'd have to take this 1/4, right? You'd have to, or sorry, you take the -1/4, and you would have to subtract 2 from it, and then you'd have to take this as a +1/4 and subtract 2 from it. But I'm never going to ask you to just look at one of these and give me domain, range, period, all that. I'm going to ask you to graph them. And then give me the information. All right, so domain, range, and then what's next? Amplitude? What's the amplitude of this? 1/4. And the period? The period you can get without, all you have to do is take the thing that's in front of x right here and take 2 pi and divide by 1/5 pi. And if you did that, you would get 10. All right, we kind of knew it from the picture already. But that's, if you did this formula, 2 pi over omega, the pi's would cancel, 2 over a fifth, the 5 would pop up with the 2 and become a 10. We good? Sure? Okay. By the way, while we're talking about graphing these things, you know, you may ask yourself, why, right? Why do I need to graph these? I'm never going to need to graph these, and if I ever do, I just have a computer graph them for me, and with technology the way it is today, this seems kind of ridiculous that we're doing this. Right? Kind of? So what do you think I mean, why is it still important for us to graph these by hand?
So we understand how to read the graphs?
Yeah, I mean, there's details in here that you couldn't understand from just typing it into a computer. But this goes back to one of the more fundamental questions that I may or may not have addressed with you already, which is just the idea of just learning in general. and your ability to absorb information. I mean, a lot of what you do in college is about, can you learn? Is your brain capable of taking in information, processing it, and then being able to demonstrate that you understand that concept to somebody else? Right? So that if I hire you, right, we're gonna get philosophical here. The difference between a person with a degree and a person without a degree. You may find somebody who doesn't have a degree who's brilliant. There's plenty of brilliant people in the world that don't have degrees and they do well for themselves. The degree, in my opinion, what it does is it tells an employer that you're learnable, teachable, whatever. That you can learn, right? Even if it's stuff that you don't enjoy, you can learn it. That's what the degree shows. And so that when you have two people sitting there, you know nothing about this one person who's supposed to be really smart, and you have this other person who has a degree, are you willing to take the risk on the person you know nothing about? Are you willing to take that piece of paper, and that paper means that when you go to sit this person down at this machine and teach them how to do this, or show them this software program for the first time, are they going to take a year to figure it out, or are they going to be able to absorb that and get the information in 2 weeks? Does that make sense? This is what it's about. If your attention span is like 2 minutes, you're not employable. You know what I'm saying? So it's not about the graphs. It's about, can you sit there and process, demonstrate. And problems like this are good because they make you have to think about multiple steps. And as you progress through calculus, it just gets, the problems get longer and more complicated. And again, that's just testing your ability to think. All right? That's my 2 cents on it. Time to graph secant and cosecant. So we're going to move into 7.7. Secant, cosecant, tangent, and cotangent. All right. I'm actually going to start with cosecant. And then after I do cosecant, we're going to do secant. And after I do secant, we're going to do tangent. And after tangent, we're going to do cotangent. All right? So let's start with cosecant. Y equals, and we're going to start with the basic cosecant x function. Now, we all remember, hopefully, that cosecant, by definition, is 1 over sine x. Yeah? So it's basically taking whatever value you have for sine, and it's taking 1 divided by that, right? So let's take a look at sine and kind of analyze what happens, because we're like experts with sine now. Right, this is what sine looks like. And let's go ahead and mark all these points here because they're important for us to get started here. Your standard sine curve looks like this. Okay. I think there's one little experiment that I want to do with you all before we actually do this. If I tell you I have a number that is, let's say I'll take the number 1, and let's say I divide this by a small number, what is my answer going to be? Is it going to be big or small? Big? Let's see why. What's 1? Let's do a small number. How about 1/10? Is 1/10 small? That's kind of small, right? If I asked you to do this, wouldn't you just flip this up and it would become 10? Okay, what about 1 divided by even smaller number, like 1/100th? That's going to be 100. And then what's 1 divided by like 1/1000th? That's 1,000, right? So if you have 1 divided by a small number, your answer is going to get big, right? And the smaller that is, the bigger that is, right? Okay. And then the other way around is this. What if you have 1 divided by a big number? What's that going to be? Small number. As an example, 1 over 2 is 2 pretty big? 2 is not that big, but that's what, 0.5? That's smaller. What about 1 divided by 10? 0.1, that's smaller. 1 divided by, let's go to 10,000, right? Very small, 0.000, whatever. So as the denominator gets bigger, the fraction gets smaller. If the denominator gets smaller, the fraction gets bigger, right? So it's like an inverse relationship. Let's use that right here to try and figure out what the heck's going on. Let's make a good old t-table. I'm going to change colors from blue to purple here. If I want to graph cosecant x on a t-table, if I plug in, here's x, here's cosecant x, let's try and plug 0 into this function and see what happens. Well, by definition, isn't this 1 over sine of 0? And what is sine of 0? Here's the graph right here. What is sine of 0? 0, right? So this is going to be 1 over 0. And division by 0 is undefined. So right away, right out of the gate, we have a problem with cosecant, don't we? It's undefined at 0. So you know how we had this great scenario where when we were talking about sine and cosine, the domain was everything? We had no problems? Right away, cosecant has a problem at 0. Because if you try and plug 0 into this, that means 0 here, that gives you division by 0, and that's undefined. That means when we go to try and graph cosecant, at 0 there will be no graph. Right? Okay, let's move to the next point. How about pi over 2? That's interesting. So what's happening at pi over 2? So that's 1 over sine of pi over 2. And what is sine of pi over 2? 1. So this is 1 over 1. What's 1 over 1? 1. So if I plug in pi over 2 into my cosecant function, it spits out the number 1, doesn't it? Doesn't that mean that my purple graph here has a point right there? The sine function is just up here as a guide for us, all right? That's all it is. The purple is the actual graph of cosecant. All right, let's try and move on to pi. What happens at pi? Well, 1 over sine of pi. Sine of pi is what? 0 again. We're undefined. Crap, we've got some serious issues here. At pi, our cosecant function is undefined, which means we don't have any graph at pi. How about at 3 pi over 2? That's 1 over sine of 3 pi over 2. What is sine of 3 pi over 2? Negative 1, right? 3 pi over 2 sine is negative 1. So 1 divided by negative 1 is negative 1. So I have a point there, don't I? At 3 pi over 2, the cosecant function is here now. And then let's try 2 pi. What do you mean, same thing? Bad stuff, right? Here, undefined. So far, I tried to pick the same points I used for sine, and I was only able to get 2 points that were worth any value to me at all, right? So what the heck does this thing look like then? Well, let's try something. Let's take just, I want you to think about what would happen here. If I take a number, I'm not going to tell you what it is. If I pick something right here that's smaller than pi over 2, and I plug it in to sine, I'm going to get a number out, right? That number is going to be smaller than 1. Agreed? Smaller than 1. What if I took that and I did 1 over it?
It's bigger.
It's going to be bigger than this number, isn't it? So I'm just going to pick like an example. Let's say I plug this in and I got out here 0.8. Let's just say I did, right? 0.8. Then if I did 1 over 0.8, that would be cosecant. And if you do 1 over 0.8 and flip it, well, you'd have to do 0.8 is 8/10. And then you flip it, you get 10 over 8. And then you would get like 1 point something. It would be bigger than 1 though, wouldn't it? So that means that when I plug this value into cosecant, I get a value that's bigger than 1, right? Bigger than 1. What if I pick another point right here, like right around in here? Into sine, it's going to be smaller, isn't it? And then when I do 1 over that, it's going to be bigger. So that means when I plug this point into cosecant, it's going to be bigger than this one was, right? Now, can I get closer? Can I pick a number even closer? And that's going to be even smaller, which when you do 1 over it, it's going to be even bigger, right? So it's got to be even bigger than this one. Am I ever going to run out of points? If I keep moving towards 0, will I ever run out of points? No, because you can always, it's this theory of, let's say the tray here is the number line, right? And let's say the seat represents 0. If I'm starting to get closer to 0, I can always just go halfway and then take half of that and then half of that and half of that and half of that, and I will never get to 0. So you can pick an infinite number of points moving towards 0 and keep plugging them in. They're going to keep getting smaller, aren't they? And that means 1 over them is going to keep getting bigger. So what's happening as I draw this picture to the left? It gets infinitely big, doesn't it? However, it never gets to 0. Okay? Like you can never be 0. So you have this thing here that you had in college algebra. We called them vertical asymptotes. Remember those? You have this vertical asymptote like this that you can never actually be there, right? But your cosecant function can get closer and closer, and it just keeps getting bigger and bigger. So you have this idea of a vertical asymptote like that. Make sense? Okay. Now, what if I had done the same thing but moved this way? If I pick a point here, that number right there is going to be a little less than 1, and then 1 over that will be a little bigger than 1.
Correct.
And then, kind of, I don't want to say that, but then here goes here. That number's smaller than that one, but that means 1 divided by it will be bigger, right? And I keep doing that, and I keep moving towards pi. Now pi, I had a problem at pi, didn't I? At pi was undefined. So as I get closer and closer here, 1 over that gets bigger and bigger and bigger. So I have the same exact thing happening right here. I have another vertical asymptote. And this thing is taking off towards infinity. Now I heard parabola, and kind of. When I do the homework solutions for this and I say what to do, I say draw a little parabola, kind of like a little parabola thing in here, right? It's not a parabola, right? Because parabolas have a very special property that these don't have. Parabolas don't have vertical asymptotes. When you have a parabola, this goes to the right forever and up forever. There's no boundary ever. And this goes to left forever and up forever, right? That's a parabola. These look kind of like parabolas, but they have these two walls that they always have to be between. So that's why I won't use the word parabola. Okay, good? Yes? All right, now we knew that this point right here was part of our cosecant graph, right? Okay, so I'm going to ask you, what's your name?
My name?
Yes.
Oscar.
Okay, I'm going to ask you, since you look like you're a little tired, so I'm going to ask you, if I pick this point and I plug that point into sine, what will I be getting?
Sine?
Into sine. Am I getting small positive number, small negative number, a big negative number, big positive? What am I getting? Okay, you should not be laying down and closing your eyes in this class. Okay, if you're tired, go walk around, all right? But unless you're at the point you can answer that question, you shouldn't. All right, so I'll ask everyone. If I plug this into sine, what am I going to get? A small negative number, right? Less than 1. So when I do cosecant 1 over that, I'm going to get a bigger negative number. So that means it's going to be like down here. And then what happens is if I start moving closer and closer to pi that way, these get smaller and smaller negative, right? 1 over that gets bigger negative. So it's going to start looking like this. And then if I start moving this way, look at my sine values. My sine values are getting smaller in negative, which means cosecant, the reciprocal, should get big in negative. So it should do this. And I'm going to have another vertical asymptote right here. That's supposed to look like a U, not a little corner, but that okay? This should look more like that than this, all right? That's it. The purple graph is the graph of cosecant. It is a very different looking function than sine, isn't it? But we can basically build the entire function. I could graph this purple by just knowing the blue. Let me illustrate. If I needed to do another period, of this, it would end here at 4 pi, wouldn't it? And then this would be 3 pi. And then who cares what those are, okay? My sine function would come in here and repeat itself, wouldn't it? Like this. And what I know is that anywhere that sine was 0, I had vertical asymptotes, didn't I? So I know automatically I'm going to have another vertical asymptote here, and I know I have another vertical asymptote here. And I also know that for the cosecant function at this top of this hump, 1 over that is 1 over 1, which is itself. So I know I'm going to have my cosecant will be part of that and be part of that graph. So these 2 points must be there. Yes?
So they're actually, both graphs are actually touching?
Touching, yes. They are touching each other at this point.
Okay.
Yep.
1 point.
At only 1 point. There's only 1 point that sine and cosecant share in common on this little interval. On that hump, it's just that the top of sine touches the bottom of the cosecant right there. And so I'm going to repeat this. I'm just going to draw a little parabola-looking thing in here, okay? And that's my graph. We do not have an idea of amplitude anymore, because amplitude was like up and down, right? Like the top of the wave and the bottom of the wave, like that's how we were determining how to get the amplitude. How about let's talk domain and range. That's a little harder. But do you get how I got that graph? Okay? We're going to do secant the exact same way. But let's talk about domain and range of this. And then we're going to start graphing them. This is just to kind of get you to understand what's happening, all right? So domain. Domain's going to be tough. Domain is not as easy as it was with sine and cosine. So it looks like, and I'm talking about, just to be clear, I'm just talking about the cosecant, the basic cosecant function. There's been no changing to it, no moving it around or anything, just the basic cosecant function. The domain is, well, you've got a vertical asymptote, then you got, this is all good, right? Everything between 0 and pi is good. And then another problem, and then everything between pi and 2 pi is good, then another problem, and then it looks like we're having problems where? At every single multiple of pi, right? At pi, 2 pi, 3 pi, 4 pi, 5 pi, right? So what I could say here is that the domain is this, that x cannot be n pi. There you go. That's telling you, instead of telling you what x can be, I'm telling you what x can't be, because it's easier for me to tell you what x can't be. Now, yes?
And when you use n
n is an integer. Integer, yeah, it's yep, can't be a fraction. Yep. But it can be both positive and negative, so yeah, okay. Is there a way you could do the interval notation of this, though? Let me write it down and see if you believe it or not. Show that to you for the first time. That way you can think about it. So look at this. I used parentheses. Parentheses mean do not include the endpoints, right? Brackets mean include the endpoints. So this is saying do not include the endpoints of this interval. Oh, what? Okay, so let n be 1. Let n be 1 and tell me what that interval is. If n is 1. What do you get? You get pi, comma, 2 pi. Is this thing good between pi and 2 pi? Yeah, in here, I've got graph. Okay, let n be 2. And what do you have? 2 pi and 3 pi. Between 2 pi and 3 pi, is it good? Yes. And then what if I did n is 3? I would get 3 pi to 4 pi, wouldn't I? How about this interval? 0 to pi. How could I get that? Could I get that? If n is 0. What if n is 0? You get 0 and you get pi, don't you? So how did I create this? What was I thinking? The way I did it is I said, all right, I'm just going to look at my first little interval here. 0 and pi, right? I need it to be between 0 and pi. So I started off and I wrote down 0 and pi. And then I said, what would it take to move that and just jump it over here? I would have to jump the 0 by pi and jump the pi by pi, right? So all I did was said, I need to jump from 0, I need to jump by some multiple of pi. I need to, the other endpoint, jump by some multiple of pi. So if you want to take this interval 0 pi and jump it 4 times, 1, 2, 3, 4, I'll be here. You see that? Now, this is acceptable. But this is something more, if you've advanced through like calculus, you need to be able to think more in terms of this than this. This is easier to do than this, would you agree? But once you understand this, this is not, am I too terrible, I don't think? Did I have to use 0 and pi? Could I have started somewhere else? I could have started at 2 pi and 3 pi. Because negative integers, then if I plug in negative n's, it's going to take me back. And positive will take me to the right. So it didn't matter where I started, as long as the 2 points were next to each other. Okay, that's domain. How about range? Range is a little tougher. Because you have a gap, right? So what we know is that these graphs, they go down forever, right? So negative infinity, we're coming up until we get to where? This right here is negative 1, isn't it? So my range goes from negative infinity to negative 1, close bracket. So the bracket is on the negative 1, because do I actually make it to negative 1? Yes, I do. And we always put parentheses on infinity. Never put a bracket on infinity. Why? Yeah, infinity is not a number, right? It's this idea that it continues forever. All right, that's not the whole range though, because I also get values from 1 up. So I'm going to put the union symbol between, and then I go bracket 1 to infinity. So that's your range. Does that answer make sense? Okay. Amplitude, throw it out the window. We don't have an idea of amplitude with cosecant. Period. Well, does it repeat itself? Like it does this, then that, right? And then it does it again, this and then that. How far along does it do it? 2 pi again, right? It turns out that the period of cosecant is identical to the period of sine. So whatever it was for the sine is going to be the same for the cosecant. So this period will be 2 pi. You doing all right? All right, before I get to secant, we're going to do a tough cosecant problem. And then we'll go and look at secant, okay? So here's what I'd like for us to do. I'd like for us to graph, as an example, y equals -1/4 cosecant, I think it was 1/5 pi x minus 2. I'm throwing you right into the fire, okay? I'm not even going to wait or hesitate or anything. You're going into the fire. Now that should look familiar. Does that look familiar to you? That's the problem we just did, isn't it? The problem we just did was sine, not cosecant, right? So how do we graph this? Well, I'll tell you how you graph it. It's actually pretty convenient. What you're going to do is you're going to just change this to sine. And you're going to graph that. All right? Which we've already done. Okay, so I'm going to just slap it up here real quick, if I can remember all the details of it. We had -7/4. No. Was that it? Yeah. -9/4 down here. And then -2 here, right? And then it started out, let me see, I believe it went, it was 10, 5, 5 halves, and 15 halves, right? And it was here, here, here. This doesn't look right. Was this right?
Yeah.
Yes? For some reason something doesn't seem right to me here. Was that our graph? Look back. Was that our graph?
We did cosine.
Oh, was it cosine? Shit. It was cosine. Damn it. Okay, well, we have to wait. We can't do it. We can't do it this way. I thought we graphed sine. It was cosine? Ugh, we can't do this. That means we have to graph it. We have to graph this one. Okay, but I think we can move kind of quick through this one, okay? I think we can. And it's good practice. Oh, well. All right, so I am not graphing this right now. I am graphing this right now. All right? Okay, so to graph that, I set the argument equal to 0. I'm moving quickly. Just tell me if I need to slow down. 1/5 pi x equals 0. 1/5 pi x equals 2 pi. I already know the answers to this, 0 and 10, right? Come here, number line, 10, 5, 5 halves, 15 halves, and I have x-intercepts here, 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 because it's a sine. I plug in a test point. I plug in 5 halves. When I plug that in, -1/4 sine of 1/5 pi times 5 halves. Remember, I'm ignoring the 2 right now. The 5's cancel, and this just becomes pi over 2 in here. What is sine of pi over 2? Sine of pi over 2. 1. 90 degrees. So this just becomes -1/4. So I have a point down here at -1/4. And that, by default, makes the one at 15 halves come up here to +1/4. And then I could draw it, and I'm drawing it dotted because I haven't moved it, have I? Was that too fast, or are y'all all right with that? Okay? Now I need to move everything down 2, right? I already know what these values are because I've already subtracted 2 from that earlier. And I think I'm going to go with a black marker here. I have like -9/4. I had -2 and -7/4. Y'all agree? All the points get moved down 2. So this one goes here. This one goes here. This one on the x-axis goes to -2. This one goes to your +7/4, and this one goes to -2. So you've got this picture. Ah, terrible. I understand I'm moving fast. Do you understand it, though? Any questions on this up to this point? I'm ready to draw the cosecant now. How do you think I'm going to draw the cosecant? What do you think I'm going to do? I'm just going to draw my little parabola things. That's all I'm going to do. The question is, where do I put them? Well, this right here is this right here, right? Where did I have the vertical asymptotes? Where would they be? At the x-intercepts here, here, and here, right? So that means I have a vertical asymptote here, like this. I have another one here. And of course I had one at the origin, which was right there, right? Here comes cosecant in purple. Point at the bottom of that, parabola-looking thing going down. Point at the top of this one, parabola thing looking thing going up. And there is cosecant right there. Well, that's not cosecant. That is -1/4 cosecant of 1/5 pi x minus 2. So I guess what I'm here to tell you is that there's really no difference in graphing cosecant than there is in graphing sine. There's just that one added element that at the end you got to just draw these little parabola things instead and draw vertical asymptotes. Yes? So if I came back in here and took everything else off the graph, like all my little intermediate work, right? You could even take out the verticals because they're not really part of the graph. They're just there as a guide for us. That's the graph of cosecant right there. That's one period of the cosecant of that cosecant function. But I want to see all the detail. I want to see all your little dotted graphs in there. That to me shows me, again, that I could teach you how to use a copying machine that wouldn't take you 4 months to learn how to do it. You know, I see all the steps. All right, let's take a look at secant function. I'm going to go a lot faster through the secant function because if you understand cosecant, secant follows through pretty well. So y equals secant of x, which is the reciprocal of cosine of x. So to try and get an idea of what it's doing, I'm going to draw cosine first. Cosine still had some important stuff going on between 0 and 2 pi. But it had its x-intercepts here and here. And then the standard cosine function started out up top here, down through, and then it came back up, and then back up like that. So there's your cosine. So if you had to take a guess here as to how I would draw secant, what do you think I'm going to do? To start, what do you think I'm going to do? Okay, so you want me to put some points? You want to draw that? Okay, good. Let's start with the asymptotes. Where would the asymptotes be for this function? At pi over 2 and 3 pi over 2, right? So wherever I see those intercepts, I'm going to draw my asymptotes